Have you ever really stopped to think about well, how deeply energy is just woven into everything you do every single day?
Mm.
You flip a light switch, your car starts up, phone's charging. It's all energy doing the work. But what is it, really? How does it actually function?
It really is
Yeah.
everywhere, isn't it? I
Yep.
mean, our entire quality of life, even just basic sustenance, it hinges so much on having energy available.
Yeah.
And, to really get a handle on our modern world, the challenge is, too, you kind of need to understand where energy comes from, how it changes, and, well, the consequences.
Absolutely. So that's our mission in this deep dive. We want to give you a shortcut, sort of, to getting properly informed on the basics of energy.
Hmm.
We'll unpack what it is, how it moves around, and its huge impact from your home right up to the whole planet. We've pulled out some really fascinating insights from our sources. Think you'll have some real aha moments.
Sounds great.
Okay, let's get into it.
So first off, energy isn't just one thing. It shows up in loads of different forms.
Yep.
You got thermal, that's heat, mechanical, electric, chemical, nuclear.
Right.
And what's really mind-bending, even mass itself is a form of energy. Thanks, Einstein.
Ha, yeah, EM secret.
Exactly. Now, when we look at a system, like, say, a machine or even just a room, we tend to talk about energy in two main buckets, microscopic and microscopic.
Okay, so macroscopic, that's the stuff we can sort of see and measure easily, like a car driving.
Precisely. Macroscopic energy is the energy the whole system has because of its motion or its position. Kinetic energy is a big one, the energy of movement.
Faster it goes, more energy.
All right, and the heavier it is, too. Then there's potential energy, which is stored energy. Think of water held back by a dam. It has potential energy because of its height.
And we harness that directly, don't we? Like with wind turbines. I saw in our sources a steady wind, maybe 8.5 meters per second, has a specific kinetic energy,
Yeah.
36.1 joules per kilogram.
Yeah, that sounds about right.
And a decent-sized wind turbine, maybe 12 meters across, could potentially generate something like 41.7 kilowatts from that moving air alone.
Pretty impressive when you think about it that way. Now, the other side is microscopic energy. We usually call this internal energy, symbol U.
Okay.
And that's the sum of all the tiny, tiny energy forms related to the molecules themselves, how they're structured, how they're moving around.
So down at that invisible level, what's making up this internal energy?
Well, it's quite a mix. There's sensible energy, which is basically the kinetic energy of the molecules bouncing around, spinning, vibrating.
Ah, so that's related to temperature.
Directly. Higher temperature means those molecules are zipping around faster, more sensible energy. Then you have latent energy.
Latent, hidden.
Sort of, yeah. It's the energy tied up in changing phase, like ice melting to water or water boiling to steam. You're putting energy in to break the bonds between molecules, but the temperature isn't necessarily changing during the phase change itself.
Got it.
And then there's chemical energy, stored in the bonds, holding atoms together in molecules. Think combustion burning fuel releases that chemical energy.
And the big one, nuclear?
And nuclear energy, yeah. That's the enormous energy locked inside the nucleus of an atom. Huge amounts. Unless you're dealing with nuclear reactions, we often leave it aside in basic thermodynamics, but it's fundamentally part of the system's internal energy.
Wow, okay, so all these forms. It leads us to maybe the most fundamental rule of all, right? The first law of thermodynamics. Conservation of energy.
The big one. Energy cannot be created or destroyed. It only changes form.
Simple statement, but the implications. Let's try that classic riddle. You're in a room perfectly sealed, perfectly insulated. You put a fridge in the middle, open the door, plug it in. What happens to the average air temperature in the room?
Ah, yes. This is a great one because it trips people up. Your first thought might be, well, it's a fridge. It cools things down.
Right, so the room gets colder.
But think about the system. If the system is the entire room, air, fridge, everything inside that sealed, insulated boundary, then no energy can get in or out as heat.
Okay, no heat transfer across the boundary.
The only energy crossing the boundary is electricity coming in through the plug to run the fridge. Now, what does the fridge do? It uses that electrical energy to pump heat from its inside compartment to the coils on the outside, right? Plus, the motor and compressor themselves generate heat just by running.
Okay, so it's moving heat around and generating some itself.
Exactly.
Yeah.
And all that electrical energy it draws in, it has to go somewhere, according to the first law. It ultimately gets converted into thermal energy and dissipated into the air inside the room.
So the room actually gets warmer.
The room temperature increases. Counterintuitive, but it follows directly from energy conservation.
That's the aha. moment then. It shows that when we talk about saving energy in everyday life, like turning off lights, we're not really talking about destroying energy.
No, you can't destroy
We're
it.
talking about preserving the quality of
Yeah,
energy, right?
precisely. That's a fantastic way to put it. Think of high-quality energy like electricity. It's very ordered, very useful, can do lots of work. Low-quality energy is like low-temperature heat. It's very disordered, random molecular motion.
Like dropping a box of organized files and having paper scatter everywhere.
Good analogy.
Yeah.
You can easily convert organized energy, electricity, into disorganized energy, heat, like that fridge warming the room. But going the other way, turning disorganized heat back into useful, organized work. You can only ever convert a fraction of it. You always lose some quality.
Okay, that distinction between quantity and quality is crucial. And speaking of huge energy, back to nuclear for a second. Fission splitting heavy atoms like uranium-235, that's nuclear power plants, submarines.
And the energy release is just immense. Our sources mention 1 kilogram of U-235 releases the same energy as burning, what was it, 3,700 tons of coal?
Wow, that's staggering. But the big catch is the waste, right? Safely dealing with radioactive byproducts.
That's the major challenge, absolutely.
Yes.
Safe, long-term storage is critical. And then there's fusion, the opposite process, combining light atoms like hydrogen, which powers the sun.
Even more energy potential there?
Potentially even more, yes, and with less problematic waste. But the conditions required are just extreme temperatures like 100 million degrees Celsius.
Yeah.
Making that happen in a controlled, sustainable way on Earth is, well, it's one of the biggest science and engineering challenges we face.
I saw this wild thought experiment in the sources. If you could somehow run a car on U-235, just 0.1 kilograms, like a small fistful, could theoretically power it for 138 years.
Yeah, I saw that. They quickly add the caveat that it's not realistic because you need a certain amount of critical mass for fission to happen properly.
Right, can't just pop a tiny pellet in.
But it does hammer home just how incredibly energy-dense nuclear fuel is compared to, say, gasoline or anything else we typically use.
Okay, so we've got a sense of what energy is, its different forms. How does it actually move? How does it get from A to B or change things?
Good question. For a closed system, one where no mass crosses the boundary, the energy can only get in or out in two ways, as heat or as work.
Heat or work. That's it.
For a closed system, yes. If you have mass flowing in or out what we call a control volume, like a jet engine, then the mass itself carries energy with it. That's a third way. But let's focus on closed systems for now. Heat and work.
Okay, let's clarify heat then, because we use that word all the time, maybe loosely. What's the strict thermodynamic meaning?
It's very specific. Heat is energy transfer. That happens only because there's a temperature difference. It always flows from the hotter thing to the colder thing.
Always hot to cold.
Always. And once the temperatures equalize, the heat transfer stops. It's important to distinguish this transfer, which is heat, from the stored energy within an object due to its temperature, which is thermal energy.
So a hot coffee cup has thermal energy, and it transfers heat to the cooler air.
Perfect. You got it.
And if something is adiabatic, that means no heat transfer.
Correct. An adiabatic process means zero heat crosses the boundary. This could be because the system is really well insulated, like a perfect thermos flask, or maybe because the system and its surroundings are already at the same temperature, so there's no driving force for heat to move.
Interesting. Didn't people used to think heat was like a fluid?
They did. For a long time, the caloric theory proposed heat was an invisible fluid called caloric that flowed between objects. But experiments, especially by Count Rumford boring cannons and James Joule stirring water, showed that heat was actually related to motion and work. It wasn't a substance itself. That paved the way for our modern understanding.
Okay, so if energy transfer isn't due to a temperature difference, it must be work.
That's the definition. Work is any energy transfer across the boundary that isn't heat. It's usually caused by a force acting over a distance.
Examples.
Think of a piston moving in a cylinder, compressing a gas. That's work being done on the gas. Or a rotating shaft, turning a generator. That's work being done by the shaft. Even electricity crossing a boundary to power a device is considered electrical work.
Right. And you mentioned earlier heat and work are boundary phenomena.
Yes, and this is critical. You only observe heat or work as they cross the boundary of the system you've defined. They have properties stored within the system, like internal energy is, and they're path functions.
Meaning, the amount depends on how the process happens.
Exactly, like climbing a mountain. The change in your elevation, potential energy, only depends on the start and end points. But the effort, The work you do depends on the path you take, steep and direct, or long and winding. Same with heat and work in thermodynamics.
That system definition seems key. Let's use those examples from the sources. A candle burning in a perfectly insulated room. System, room plus candle. Is there heat transfer?
If the room is truly perfectly insulated, then the boundary doesn't allow heat across. So technically no heat transfer across the boundary. It's adiabatic for the whole room system.
But energy is changing inside, right?
Oh, absolutely. Chemical energy in the candle wax is converting into thermal energy, sensible energy, in the air and the candle itself. The internal energy of the system increases, but it happens within the boundary, not by heat crossing it.
Okay. Now, the oven example. System is the entire oven, including the heating element. Heating it up, is that heat or work?
If the whole oven is the system, energy comes in as electricity crossing the boundary to the heating element. That's electrical work being done on the system.
Right. But now, change the system boundary. System accounts only the air inside the oven. The heating element is now outside this system.
Now, energy flows from the hot element outside the system to the cooler air inside the system because of the temperature difference. In this case, with this system definition, it's classified as heat transfer.
Wow. So the exact same physical process can be called work or heat, depending entirely on where you draw the imaginary line for your system.
Precisely. It highlights why being absolutely clear about your system boundary is the first, most crucial step in any thermodynamic analysis. Heat and work are interactions at the boundary.
That's a really powerful illustration. Okay, besides those general concepts, what about specific types of mechanical work we see often?
Well, shaft work is everywhere. Engines, turbines, pumps. Our sources have that example.
All right.
A car shaft spinning at 4,000 RPM with 200 Newton meters of torque is transmitting 83.8 kilowatts of power. That's work.
Okay.
Then there's spring work energy stored when you compress or stretch a spring, and also just the basic work needed to lift something against gravity or to accelerate it.
Like pushing that cart uphill, that took, what, 67 kilojoules?
Yep, 67 kilojoule to get a 200 kilogram load up a 100-meter 20-degree slope. That's the work needed to increase its potential energy.
Or accelerating a car, getting a 900-kilogram car to 80 kilometers in 20 seconds requires 11.1 kilowatts of power just for the kinetic energy change.
Exactly. These calculations show how thermodynamic principles apply directly to everyday mechanical actions.
Okay, this feels like a good point to shift gears slightly and talk about something everyone's interested in, efficiency. We hear high efficiency this, energy efficient that. What does it actually mean?
Fundamentally, efficiency is simple. It's what you want to get out divided by what you have to put in. Desired output over required input.
Simple ratio.
Simple ratio, yes, but the devil is in the details, as they say. You have to be super clear about defining that output and input. Our sources stress this because efficiency can be misused or misunderstood if the terms aren't defined properly.
Let's make it concrete. Water heaters in our homes.
Great example. An electric water heater might boast 90–94% efficiency. A gas one might be more like 55–62%.
So electric wins? Easy choice.
Not so fast. That efficiency number is usually about how much of the energy input, electricity or gas, actually ends up in the water as heat. Electric resistance heating is inherently very good at converting electricity to heat, hence the high number. Gas heaters lose more heat up the flue.
Okay.
But, and this is a big but, the cost of the energy matters hugely. Natural gas is often much cheaper per unit of energy than electricity. So even though the gas heater is less efficient in converting fuel to hot water, it might actually cost you less to run.
So efficiency percentage isn't the whole story for my wallet?
Exactly. You need to consider the source energy cost as well. It's about the overall operating cost, not just the technical efficiency number in isolation.
Makes sense. What about lighting? That feels like an area where efficiency has really changed things.
Oh, massively. Think about old incandescent bulbs. They were terrible. Maybe 6 to 20 lumens of light for every watt of electricity. Most of the energy just went out as heat.
Right, they get really hot.
Then came CFLs, compact fluorescence, much better, 40–87 lumens per watt, and now LEDs. They're fantastic, potentially up to 160 lumens per watt in some cases.
That's a huge jump.
It is. The sources give a great practical comparison. A 15-watt CFL gives about the same light as a 60-watt incandescent, and it lasts maybe 10 times longer. The savings on your electricity bill and on buying fewer bulbs really add up. That's efficiency paying off directly.
And cooking. Similar story with electric versus gas.
Pretty similar pattern, yeah. Electric stovetops are generally more efficient at transferring heat to the pot, maybe 73% versus 38% for gas burners. But again, that cheaper cost of gas might make it the more economical option for cooking in many places.
And things like microwaves or convection ovens?
They are inherently more efficient because of how they heat the food. Microwaves target the water molecules directly, and convection ovens circulate the hot air, cooking more evenly and often faster, using less energy overall compared to a conventional oven just radiating heat.
This really drives home the economic benefit of choosing higher efficiency. The numbers can be quite stark.
They really can. Take industrial motors, for example. Let's say you swap out an old 60 horsepower motor that's 89% efficient with the new one that's 93.2% efficient.
Okay, doesn't sound like a massive leap, 89 to 93.2.
Doesn't sound huge, no.
Yeah.
But if that motor runs a lot, say 3,500 hours a year, that small efficiency gain saves nearly 8,000 kilowatt hours of electricity annually.
Wow.
At maybe 8 cents per kilowatt hour, that's over $600 saved every year.
Yeah.
And if the price difference for the better motor was only, say, $640,
It pays for itself in just over a year.
exactly, a payback period of basically 1 year, makes it a very smart financial decision besides the energy saving itself.
So these efficiency principles apply across the board. Pumps, turbines, generators, they all have losses, and improving them helps.
Absolutely. And often you have devices working together. Like in a hydroelectric plant, you have the efficiency of the turbine capturing energy from the water and the efficiency of the generator converting that rotation into electricity. You multiply those together to get the overall plant efficiency.
So maybe the turbine is 77.6% efficient, and the generator connected to it adds its own losses, bringing the combined efficiency down to, say, 72.7%.
Something like that, yeah. It shows that even in big, well-engineered systems, there are always steps where some energy quality is lost in the conversion process.
And the crucial link here, beyond the economics, is the environmental one. Saving energy means
It directly means reducing pollution. Less energy used means less fuel burned, whether it's gas in your furnace, coal, or gas at the power plant making your electricity. That means fewer emissions of things like CO2, which drives climate change, but also NOx and SO2, which cause smog and acid rain.
which brings us squarely to that environmental footprint. Because as useful as energy is, converting it, especially from fossil fuels, has major consequences. Smog, acid rain, climate change.
Yeah, these are the unavoidable side effects, the hidden costs of our energy system. Smog, that hazy stuff in cities, is mostly ground-level ozone. It's nasty stuff.
How does it form?
It's mainly hydrocarbons and nitrogen oxides, NOx reacting in sunlight. A lot of those come from vehicle exhaust. Smog irritates your eyes, damages lungs, makes asthma worse. And then there's carbon monoxide, COO, also mainly from cars. It's poisonous because it interferes with oxygen transport in your blood.
But things have improved there, haven't they? Thanks to things like the Clean Air Act.
Definitely. Our sources point out that emissions of those specific pollutants have decreased significantly in places like the U.S. since the 1970s due to regulations on vehicles and industry.
Okay. And acid rain. That was a big issue, too.
Still is in some places. It's caused mostly by sulfur dioxide, SO2, from burning high-sulfur coal, especially in older power plants, and also nitrogen oxides. These gases react in the atmosphere with water to form sulfuric and nitric acids.
And that falls down and harms lakes, forests.
Lakes, forests, kills fish, damages trees, even erodes buildings and statues made of marble or limestone. Again, regulations like the Clean Air Act have helped reduce SO2 and NOx significantly, leading to less acid rain than decades ago, but it hasn't vanished completely.
Now, the really big one everyone talks about,
Yeah.
the greenhouse effect and climate change. The sources use that analogy of a car in the sun.
It's a great starting point. Sunlight comes through the car windows easily, warms up the seats and dashboard, they radiate heat back out, but it's infrared heat, and the glass traps a lot of that infrared inside, so the car gets hot. Earth's atmosphere does something similar. Certain gases, water vapor, CO2, methane, NOx act like that glass. They let sunlight in, but they trap some of the outgoing infrared heat. This natural greenhouse effect is actually essential. It keeps Earth about 30 degrees C warmer than it would be otherwise, making life possible.
So the effect itself isn't bad.
No, it's vital. The problem is we're thickening that blanket by adding extra greenhouse gases, disturbing the natural balance.
And the main culprit is carbon dioxide, CO2, from burning fossil fuels, coal, oil, gas, and also deforestation, cutting down trees that would normally absorb CO2.
That's the core issue. CO2 levels are way up. Our sources mention around 400 parts per million now, which is roughly 30% higher than pre-industrial times, maybe a century or so ago. And projections show it could hit 700 ppm or more by 2100 if we don't change course significantly.
And more CO2 means more trapped heat, a warmer planet.
Exactly. We've already seen about half a degree Celsius of warming in the last century, and projections point towards maybe 2 degrees C or more by 2100. That might not sound like a lot, but averaged over the whole globe, it's enough to cause major disruptions.
Like,
More extreme weather heat waves, heavy rainfall, stronger storms. Rising sea levels as ice melts and water expands. Big impacts on ecosystems, agriculture, water supplies, potentially spreading diseases. It's a complex web of effects.
which is why there are international agreements like the Paris Agreement trying to limit that warming to well below 2 degrees, ideally 1.5.
Exactly. Those agreements aim to coordinate global efforts to reduce greenhouse gas emissions.
Now, related to emissions, electric cars are often touted as zero emission. How accurate is that picture?
Well, it's nuanced. It's true that an electric vehicle, or EV, produces zero tailpipe emissions. There's no exhaust coming out the back while you drive.
Which is great for local air quality in cities.
Absolutely.
Yeah.
But the car needs electricity, right? And where does that electricity come from? If it's generated by burning coal or natural gas at a power plant.
Then the emissions are just happening somewhere else, at the power plant instead of the tailpipe.
Precisely. The pollution is shifted, not eliminated. An EV is only truly zero emission. In the broader sense, if the electricity powering it comes from renewable sources that don't produce greenhouse gases like hydro, solar, wind, or geothermal power.
So the cleanliness of the EV depends heavily on the cleanliness of the electricity grid feeding it.
That's the key takeaway. It's a system-wide view you need.
Okay. So wrapping this all together, given the environmental impacts, what are the most effective ways forward? What can actually make a difference?
It really comes down to a three-pronged approach, essentially. One, conservation, just using less energy in the first place. Two, efficiency, getting more useful output from the energy we do use. And three, shifting our energy sources towards cleaner, renewable options.
All three are important.
Absolutely. And they reinforce each other. Our sources had a great example of a geothermal heating system.
Right, using heat from the earth.
Yeah. It was saving about 18 million therms of natural gas a year compared to conventional heating. And the emission savings were huge, avoiding something like 85,000 kilograms of NOx and 120 million kilograms of CO2 every single year.
Wow, 120 million kilograms of CO2.
Yeah.
That's equivalent to taking.
Thousands of cars off the road, just from that one change in how heating was provided. It shows the scale of impact that switching sources and improving efficiency can have.
That really is a powerful example. So we've covered a lot of ground today, really peeled back the layers on energy, from the basic forms, how it moves as heat and work,
To the critical role of efficiency and these unavoidable environmental consequences we have to grapple with.
Hopefully understanding these concepts helps you, our listeners, make more informed choices, whether it's picking out a new appliance or just thinking about the bigger picture of energy policy and climate solutions.
Yeah, having this foundation really does empower you to better understand the energy discussions happening all around us.
So here's a final thought to leave you with. As you go about your day, maybe think beyond just the amount of energy you're using. Consider its quality, too. And that unseen journey it took from the power plant or the oil field or the wind farm all the way to your light switch or your gas stove. Now that you have this deeper understanding, what choices, maybe even small ones, might you make to influence that energy landscape around you?